Okay, thank you. Right, next one, please, Kate. So this is our topic today, calculating customized UARL for the system, a zone, or a DMA, and how we can use FAVAD, fixed and variable area discharges, knowledge of pipe materials, and pressure burst frequency relationships to get a better targeting. It's a good day and welcome to everyone, wherever you are in the world, and thanks to Gary, Stuart, and the IWA Water Loss Specialist Group for their excellent webinar initiative this year. And thanks to you for your interest in joining this one. My main field of activity now is research, to continue to improve the concepts we use in modern leakage management, and to spread the results as widely as possible through the free-to-all Leak Suite Library website and through training materials in modern media formats. I'll be explaining the research I've done to customize the 1999 UARL equation for wider use by small utilities and in the zones of larger utilities and in district metered areas, particularly those with lower operating pressures. Kate is Managing Director of Water Loss Research and Analysis Limited, the UK company which produced the UARL with SCF software which runs the calculations. She will show you some examples to demonstrate the combined effects of the key additional influences which SCF includes. And at the end, we'll be happy to take any questions you may have and provide some web links for further information should you need it. Next one, please, Kate. In the first one of the part of the webinar, I'll outline the evolution of the UARL since 1995 and the assumptions that we used to summarize multiple influence on leakage into a relatively simple linear standard equation for UARL. This equation is now used in many countries worldwide as the basis for calculating how low you could go with leakage and for the calculation of the infrastructure leakage index. When introduced in 1999, lower limits for system size and pressure were set for use of the UARL equation. I'll show you some ILIs less than 1, which have been reported by large utilities in 2 of the best performing countries at relatively low pressures, and also some low ILIs in small systems less than 5,000 service connections. I'll then explain the 3 additional factors which I've used collectively to optionally customize any individual UARL calculation using a system correction factor, SCF, which varies with pressure, and the key takeaways will then be summarized. Kate will then show examples of UARL with SCF calculations, which demonstrate how pipe materials, system size and pressure can be key influences not only on the UARL in small systems at lower pressures, but also in other systems at higher pressures as well. The UARL equation and ILI were developed by the first IWA Water Loss Task Force using the foundation concepts of component analysis of leakage, bursts and background estimates, and fixed and variable area discharges, FAVAD. 27 diverse systems in 20 countries were used to test the methodology. UARL predicts how low could you go with leakage in whole systems with diverse characteristics of mains length, number of services, meter location on service connections, and pressure. Originally limited to systems with more than 5,000 service connections, UARL assumes a simplified linear relationship between pressure and leak flow rate. Now, relationships between pressure and burst frequencies didn't exist in 1999, so we had to use fixed burst frequencies based on international data, standardized for 50 meters pressure, and we use those whatever the pressure. So that is something that was missing from the original UARL equation. This is a very nice slide, I think, to show the how it works. It basically says a UARL will depend upon what your length of mains is, what your service is, what your length of private pipes is, and what the pressure is. It's in the metric version in cubic meters per day, and we also include in there the total length of the underground private service connections if the meter is located some distance after the property line. The leak flow rate is assumed to change linearly with pressure. Some of you will know this as N1 equals 1, and the burst frequency is fixed whatever the pressure. The coefficients of 18, 0.8 and 25 are derived from auditable assumptions for burst frequencies, average flow rates, durations, and percentages of reported and unreported bursts. Now, we're not quite sure who produced this slide. I got it from Roland Limburger, and we know that there's been several other water loss specialist group members who contributed. So I'd just like to thank all of them for putting this together to help to explain what we mean by the UARL equation. This slide now is based on an original idea by David Pearson back in about 1996. And it shows how the 4 components of leakage management are used to squeeze the current annual real losses, CARL, which you derive from a water balance, and that's the grey box. And you're trying to push it down and to achieve unavoidable annual real losses, UARL, which is the yellow box. The infrastructure leakage index, ILI, is the ratio of the 2 figures, the CARL over the UARL. And this particular diagram represents an ILI of about 4. That's to say, the current real losses are 4 times the unavoidable annual real losses. Next one, please. This slide shows sets of ILI data from 12 countries, which I've put together over the years on the Leak Street Library website. As calculations of CARL and UARL both involve some uncertainties, that they're not perfect figures ever, then ILIs are usually quoted to just 1 decimal place. Now, in the highlighted red box, you can see that Netherlands and Danish utilities with relatively low average pressures of 32 to 34 meters have been able to achieve ILI values less than 1. They're down at 0.6 and 0.7. We find that ILI data from Aqua Flanders and sample data from Germany and Austria have median ILIs of 1, and they're operating at about 39 to 50 meters average pressure. And that large Australian utilities achieved a median ILI of 1.1 in the Millennium Drought. So what this shows is that the standard UARL equation has proved to be a robust calculation for larger utility systems at around 40 to 60 meters pressure, but you have to be a little bit careful outside those limits. Other countries' median ILIs are in the range 1.7 to 4.5 at 40 to 51 meters pressure, and this indicates scope for further improvements if utilities consider it to be economic to do so or necessary for water conservation purposes. These graphs show ILIs for individual Netherlands and Danish utilities, Netherlands on the left, Denmark on the right, as blue columns. I know they're a bit detailed for you maybe to pick up, but I just wanted to pick up some points here. We have categories of performance in the left-hand vertical axis, A to D. These are being used quite widely now internationally. A is very low, that would be an ILI less than 1.5, and more than 8 would be very high. So that's the left side vertical axis. And nearly all, in fact, all the Netherlands utilities are coming in at very low performance category A1. The average pressures are shown as dots, and they're related to the right-hand vertical axes, with the pressure categories from very low, less than 30 meters, to very high, more than 80 meters. Now, we can see from that utilities in Netherlands and Denmark operate at around 25 to 45 meters pressure, and most have achieved ILIs less than 1. The Netherlands data is for utilities with 200,000 to 2.6 million service connections, and the Danish range is 4,000 to 50,000 connections. This large system data showed that further understandings of relationships between UARL and pressure was needed to take account of the sensitivity of different pipe materials, whether they're rigid or flexible. Because in pressure leak flow relationships, we have N1, which we use for quick calculations, but the true relationship is fixed and variable area, which is either N1 of 0.5 or 1.5. And we also need to take into account pressure burst relationships, which weren't included in the original equation. Next, please, Kate. Some countries have a few large systems and numerous small systems. USA, Germany, Austria, and many others. In Austria, 90% of systems have less than 3,000 service connections. And this is a very high quality data set for systems with 240 to 10,000 services, kindly provided by OBGW. It has a median pressure of 50 meters. The graph shows that a system size for below about 5,000 service connections, there's a greater scatter in the ILIs. In other words, that they can be much lower or much higher than 1. And a steep reduction in minimum ILIs as the system size reduces below around 3,000 service connections. So this small system data at an average of 50 meters pressure confirms, with other similar data, that further understanding of relationships between UARL and small system size was urgently needed. Next, please, Kate. Some of you, as the UARL and ILI concept became increasingly popular, many leakage practitioners wish to use it for analysis of leakage in smaller systems, including zones within larger utilities, DMAs, and small standalone systems like the ones in Austria. Some of you may have seen this table, which summarizes attempts to reduce the lower limits for use of the UARL equation to meet this requirement. But in fact, after 20 years now, we have to accept that it's more complicated than this. This doesn't meet the need to extend UARL to all small systems and DMAs. And there's an update of this, another column for 2020, which includes SCF, which will be shown in a later slide. Next, please, Kate. Now, let's look at research on low ILIs carried out since 1999. By 2009, it was clear that the simplified linear pressure leak flow relationship could overpredict UARL for systems with low pressures and high percentages of flexible pipes. By 2014, we already knew that in a few systems where low leak surface, UARL equation was about 20% too high. We also knew that uncertainty analysis had shown that at ILIs close to 1, the uncertainty of current annual real losses calculations from water balance could be as high as plus or minus 20%. And in systems with less than 1,000 service connections, with continuous night flow measurements, an unreported burst, even on a service, can be quite easily identified and repaired faster than allowed for in the UARL equation. So those are some reasons why you can get low ILIs. But the Austrian data shows that these explanations can't explain all low ILIs. And even though we tried to include mains length in the lower size limit, that didn't solve the small systems problem. So in 2019, I decided to look at an approach based on optional customizing, and I stress optional customizing, of the UARL equation, using a system correction factor, which includes the interaction between 3 additional factors for each individual system. Okay. So how can we customize it? Well, first of all, we can customize it for FAVAD only. In other words, rather than taking an N1 of 1, we can include the influence of pipe materials on pressure flow rate relationships. Now, also bear in mind that in the URL, we include unavoidable background leakage as well as bursts. And unavoidable background leakage makes up around 60% of the URL, and it behaves as a variable area discharge. So even if you've got totally rigid mains, you've still got a huge amount of variable area leaks sitting in your system in the unavoidable background leakage. The second option is taking into account size. And this is to use a probability distribution, which I remembered from many years ago in my engineering training, called the Poisson distribution. Now, it's the mathematics is a bit fearsome for some people, but basically what it says is if you've got rare events and low burst numbers in small systems of rare events, then you should use the median, that's the 50% exceedance probability, as being more representative of the burst frequency, let's say in a particular year. There's also a nice example about goals scored for those who like football in one of the references. It's very good for that kind of analysis. The third one is pressure burst relationships, and we can now include the influence of a general international relationship between pressure and burst, which wasn't available prior to 2013. Let's look at these in a bit more detail now. Now, many of you will be familiar with the FAVAD concept, which was proposed by John May in 1994 and is now widely used internationally. His insights into pressure leak flow rate relationships and pressure bursts stimulated my own passion for this subject 25 years ago, and he was the one who set the paths that I've tried to follow. For the fixed area bursts, such as a ring crack in a rigid pipe material, or a corrosion hole or a blowout, the leak velocity varies with the square root of pressure. The leak area is effectively fixed, so the leak flow rate varies with the square root of pressure. The green curve to the right shows that these flow rates are relatively insensitive to pressure, have a power law N1 of 0.5. However, if we have a variable burst in a flexible pipe material, where the area of the burst or leak expands with the pressure, then the leak flow rate is much more sensitive to pressure, and it follows the blue rising curve. So it's 3 times as sensitive as the fixed area leaks. And the background leakage at joints and fittings is also a variable area leakage. So that when you put together the fixed and variable area leakage and get the brown curve, particularly for large systems with higher proportions of rigid pipe materials, then you get something which approximates to a straight line. And that's why we used a linear relationship between the average pressure and leak flow rate in the original equation. But now we want to move to doing something a bit more diagnostic, because the variability of pipe materials in small systems can be much greater than in the large systems. This graph from 2009 shows, pardon me, I just have a drink. Shows how a pressure correction factor for the 1999 UARL equation could vary for the system with 100% rigid pipes. If we see that a pressure correction factor of 1 is the standard UARL equation, then we can be within plus or minus 10% of that as long as we're in the grey zone there. And if we have 100% rigid pipes, then the UARL formula sits quite nicely in that range, and we can use it from 8 meters to 75 meters pressure. But if we have 0% rigid pipes, that's 100% flexible, and all the leaks are much more sensitive to pressure, then it follows this lower curve. And that means that the pressure correction factor is within 0.9 to 1.1, only for the shorter range of 40 to 60 meters pressure. And if you go below 40 meters, it drops off very quickly. And if you go above 60 meters, then it rises up to, in that case, about 1.4. Next one, please. This graph, or this table, I should say, just shows the assumptions which we used to calculate the coefficients in the 1999 UARL equation for unavoidable background leakage. That's the second column, the second large column. the average burst frequencies that we use in the UARL at 50 meters pressure for the different components of infrastructure. If you want to look at more detail on that, the assumptions for average burst flow rates and runtimes are clearly stated and auditable in the 1999 Aqua paper, where the equation was first published. And that's accessible through one of the web links that we'll show you at the end of the presentation, for those who want to look into it. Now, we also assumed averages that 95% of mains bursts were, sorry, Kate, I slipped something else in there. That 95% of mains bursts tended to be reported, 75% of services tend to be reported, and the others are unreported. And they run for longer and have larger losses of water. The Poisson probability distribution, as I say, is used for predicting the probability of occurrence of a number of isolated events in an interval of time, when only the average number is known. So if we know that the average number is 3 service bursts per 1,000 connections per year, then we can use the Poisson distribution to look at what that would mean in any different size of system, and apply the Poisson to adjust it to give a better prediction. For those of you who like football, again, in one of the papers, I've used this to analyse goals in the English Premier League, just to show how this works. But I haven't put a lot of maths in because a lot of maths does tend to turn some people off. So the graph shows the Poisson distribution of 0, 1, 2, 3, and so on ULL bursts when the average number of bursts per year is known. So as an average of 15 ULL bursts per year, which is equivalent to 5,000 service connections at 3 per 1,000, the shape of the curve is the normal bell-shaped distribution which we expect. But as system size decreases and the distribution becomes skewed, the chances of getting less than the average number of bursts exceeds the chance of getting more than the average number of bursts. So for example, if you have a DMA with 1,000 service connections, you've actually got an average of 3 bursts per year, but you've got a 42% chance of getting less than 3 bursts and only a 36% chance of getting more than 3. And the median for this type of distribution, which is the figure which is exceeded in half of the years, becomes a better measure of the probability of burst in a single year. And the median of a positively skewed distribution like this one is less than the average when you have small numbers of bursts. Next one, please, Kate. Now, with pressure burst frequencies, if we go back to 1999, there was very little conclusive evidence of any relationship. I had some data from Welsh Water and some information from various places I'd picked up, but most people were actually skeptical that there was such a relationship. However, with colleagues from Julian Thornton's pressure management group in the Second Water Loss Task Force, we began to investigate this and to pull some data together. And the first output was the simple straw that breaks the camel's back concept in 2006. I'm not showing this here, but that's just a bit of history. What I did to get this curve is I used good quality data before and after pressure management in large zones, really large zones, during the Australian Millennium Drought in 2000 to 2011 to get this genetic form of relationship, which was published in 2013. It's since been tested and used for prediction and prioritizing PMZs in Australia, South Africa, UK, and other countries. It contains a non-pressure dependent component, BFNPD, which is the straight line, and a pressure dependent component, BFPD, that varies with the maximum average zone pressure to the power 3. Each component of infrastructure, mains, services, connections to the property line, and service connections after the property line, has BFNPD parameters based on data from high-income countries with ILIs in the range 1 to 1.5. At 50 meters pressure, the curve passes through the UARL burst frequency used in the original 99 equation. The burst frequency slowly rises between 20 and 50 meters, and then more rapidly at pressures exceeding 50 meters. So, next one, please, Kate. Slide 18, where are we now? This is where we got to with the research. There's now an optional methodology to predict the system correction factor to customize the UARL equation for any individual system, zone, or DMA. And optional checks to see if the UARL equation is likely to be out by more than plus or minus 10%, are likely to be most relevant for small systems with less than 5,000 service connections, and or systems outside the average pressure range of 45 to 60 meters. And I've amended the table underneath in the lower left corner to try to squeeze that information into that box for people who still want to use that for guidance. The right-hand table shows the parameters. I won't run through it, but there's a list of the parameters you need, whether you're dealing with the standard URL equation, plus FAVAD, plus FAVAD plus Poisson, or plus FAVAD plus Poisson, plus pressure bursts. And down in the bottom bit are the assumptions that we use for each of the 4 different options, so that they're clearly set out. So what are the key takeaways now from what I've been doing here? The first one is, I think this progresses our understanding of how low we can go by including more key factors in individual systems of any size. It also replaces the lower limits for application of the URL equation. It identifies systems at lower pressures where current targets based on standard URL may be too high and lower leakage could be achievable. It identifies systems at higher pressures where current targets based on standard URL may be too low and may need to be increased. And it also demonstrates very nicely how reductions of excess pressure can reduce both URL leakage and median burst frequencies. Okay, I'm only a few minutes over time on this, so I'll now pass you over to Kate, who will show you some examples of the calculations using the URL with SCF software.
Thanks, Alan. Good morning, everyone. Good afternoon, good evening, wherever you may be in the world. And thanks for joining this webinar today. WLRNA's challenge in this research process was to take all the interlinking concepts and equations from Alan and produce online software which could really quickly calculate the system correction factor and UARL at not only the current average zone pressure, but any average pressure between 10 and 100 meters, and be able to show the results in a user-friendly, simple format on a single screen. So this equation on screen now shows how a system correction factor, or SCF, is used as a coefficient to individually customize the standard UARL equation that Alan showed you towards the beginning of his part of the presentation. So the system correction factor is used to individually customize the standard UARL equation for each system, each zone or DMA, and takes into account now the combinations of additional factors, which you can see in these white boxes in red text at the bottom here. So these are N1 values of 0.5 or 1.5 for pipe materials, assessed from the percentages of rigid and flexible pipe materials that you enter into the calculation. It uses median burst frequencies rather than average burst frequencies, so it brings in the Poisson distribution, which Alan was talking about, and that's a very noticeable effect when you start to look at the influences on small systems. And then the pressure burst relationship for the mains and the service connections to the property line and property line to the meter. So I wanted to show you a couple of example calculations of the software. But first, I wanted to talk about how simple it is to perform a calculation. And you're going to need a maximum of 7 pieces of data for any one calculation for a whole system, a zone or a DMA. Then we're going to look at 2 example calculations. So example 1 is going to be a 5,000 service connection system, 125 kilometer mains, varying combinations of pipe materials across the mains and the services, and operating at 35 meters pressure. What we'll then do is we'll scale that example right down by a 5th. So we'll drop it down to 1,000 service connections, which is now one of our small system calculations, dropping down the mains length, dropping down the density of connections, but still operating at 35 meters pressure. And we're going to compare and contrast some of the results that we get from these calculations. And then I'm going to finish off my part of the presentation, just giving you an overview of some of the calculation, the variety of calculations we've done since UARL with SCF was released about 10 months ago for a wide range of size and different characteristics of zones and DMAs across the world. So what you're seeing on this screen is the input section for the UARL with SCF software. At the top of every calculation, you get the option to put in some particular details about the system and the utility and any other comments that you want to save along with the calculation. Underneath here, you'll see the UARL formula with the system correction factor coefficient to tailor this calculation. And then you've got system data, which are 4 inputs. These inputs are the usual figures required for a standard UARL calculation. So you have your number of services from the mains to the property line or curb stop, the average length of service connections from the property line or curb stop to meter, mains length, and average zone pressure. The 3 additional inputs here are for you to put an approximate estimate of the percentage of rigid pipe materials on your service connections from the main to the property line or curb stop, on your services from the property line or curb stop to meter, and on the mains. And there are various help links on this input screen to help you further. That's all you need for a calculation. And when you've done your calculation, it's stored online. You can access it by going online. You can also print it off or store it as a PDF. So example 1 is our larger system, 35 meters average pressure, 5,000 service connections with 20% rigid pipes, the 10 meters per connection from the property line to the meter with 50% rigid pipes on that part of the services, and 125 kilometers of mains with 80% rigid pipes. So I'm going to show you what a calculation looks like when you just put those 7 parameters in that you can see in red into the software. And what you're basically going to see is this single screen, and it may seem a bit overwhelming, but at first, because there's a lot of information on here, but I'm just going to take you very, very briefly to show you the purpose of the different areas on the screen. First, in the top left-hand side of the screen, you'll see the input section, which we've just taken a look at. That's where you put your system data in and your pipe material percentage of rigid pipes in. The rest of the screen is dedicated to showing you results, different results from the calculation. The first section we're going to look at is the bottom left results section. And this shows the numeric values for the system correction factor. Okay, so basically we're talking about this value here for the system correction factor in the corrected equation. That's what it's calculating it at, depending on whether we're considering just the effects of FAVAD, FAVAD and Poisson, and FAVAD, Poisson and pressure bursts. Underneath here, we can see the actual volumes for UARL at this operating pressure, if we're just using the standard UARL equation, or if we're using the system correction factor, considering just FAVAD, FAVAD and pressure bursts, and FAVAD, Poisson and pressure bursts. And we'll talk a little bit more about the actual numbers here in a few slides down the line. At the top of the software, you can see a bar chart, and this is to give you an indication of the median values for annual UARL bursts split across mains and services. So the bottom bar has no adjustment for bursts. It's the standard burst frequencies. And then we bring in the Poisson effect and we see how that changes the breakdown of median. These are median, not average, numbers of UARL bursts across mains and services. And again, if we bring in pressure bursts as well as Poisson and FAVAD. Okay, and you'll really see the changes here when you have a small system and you bring in the Poisson effect, or if you're operating at lower than 50 meters pressure as well. The first graph plots the values for the system correction factor against average pressure. And again, we'll look at one of these tables and graphs in a bit more detail in future slides. The table beneath just shows the numeric values which are used to generate the graph. Sometimes the lines on the graph get very close together and it's really hard to get a very accurate reading from them, and that's where the tables below really come into their own. And then the second graph and table will plot UARL and unavoidable background leakage in cubic meters per day against average pressure. And again, you've got the table below it to see those values. As you can see here, there's an awful lot of values quite close together as the pressure drops, and the table allows you to interpret that information much more clearly. So let's go back and zoom in on this results section first of all. So these are the results for 35 meters average pressure in a zone with 5,000 services. What I really want to show you here is the difference between the values calculated under a standard UARL calculation and those with the system correction factor added in. So first of all, we look at the volume 262 cubic meters per day if we use the standard UARL equation. If we just consider FAVAD, then that gives us a system correction factor value of 0.9 and corrects the volume for UARL to 235 cubic meters per day. If we now consider FAVAD and Poisson, that gives us a system correction factor of 0.81 and a volume of 213 cubic meters per day. And if we also then consider FAVAD, Poisson and pressure bursts, it brings that down to a system correction factor of 0.76 or a volume of 199 cubic meters per day. So what does that mean? It means that depending on the influences you consider when you do your calculation, the UARL could be between 10 to 24% or 27 to 63 cubic meters per day lower than predicted by the standard UARL. If we go to look at the burst frequencies for the same system, if we use the standard calculation, so no adjustment for bursts, that's this bottom bar here, then we're looking at a median number of 38 bursts per year across mains and services. The system is not a large system, it's not a particularly small system either. It's about on that 5,000 boundary where the UARL equation was recommended to be used for 5,000 service connections and above. So we do see a very small reduction if we consider the Poisson effect, and bear in mind we're considering the median number of UARL bursts rather than the average. So that reduces it from 38 to 34 per year in total across all our mains and services for this zone. This zone is operating at 35 meters pressure, which is less than the 50 meters pressure assumed in the original UARL equation. So when we bring in to the prediction for the median number of UARL bursts per year, the pressure burst relationship as well, then we see the median number of UARL bursts across mains and services reduce further down to 28 bursts per year. This is the first graph and table from the UARL calculation. So it shows us really clearly the results taking into different effects for this particular zone or system. The grey line that you can see here represents a value of an SCF of 1. Okay, so that's the standard UARL equation. Okay, we can see in at the current operating pressure, 35 meters, which is this vertical dotted blue line, that regardless of which effect we take into consideration, the standard UARL equation is overestimating our UARL. So let's look at this, each of these three lines that we can see here. The green line is the line for FAVAD, so the system correction factor value as pressures at the current operating pressure, at pressures lower than that, and at pressures higher than that. This line is reasonably flat, and for most of the time it's within plus or minus 10% of the standard UARL. That's this system correction factor value of 1. Actually, between 35 and 65 meters of pressure for this particular zone or system, then we're within that plus or minus 10% range. When we consider the Poisson effect as well, we can see that line just drop down, literally drop down underneath the FAVAD curve. And in this particular calculation, the system correction factor, when we consider FAVAD and Poisson, is only within plus or minus 10% of an SCF of 1 for 47 meters, so around about here, up to 80 meters, which is here. When we bring in the pressure burst relationship, the line curve changes considerably. What we see is how the system correction factor continues to drop quite sharply below 35 meters, but also look how it takes off once we get above about 55, 56 meters. It shoots off up here to very high SCFs, comparatively about 1.8. And if you look at the ranges under which this particular system correction factor is within plus or minus 10% of this value of 1, then the red line is only within that plus or minus 10% boundary between about 48 meters pressure from here up to 64 meters pressure up here. Okay. So overall, what we can see, or what we can take away from here, is we can see the importance of controlling average pressure. And for this particular system, if we consider the pressure burst, Poisson and FAVAD effects and calculate our UARL using them and considering them, then the UARL with SCF is only within that plus or minus 10% of the standard UARL between 48 and 64 meters. One thing to bear in mind with this calculation is, unless your infrastructure changes dramatically, your pipe materials changes dramatically, or density of connections changes dramatically, you should only need to perform this calculation once for a whole system or a DMA or a zone, because as you can see, you've got all the information here to show what would happen if you chose to increase or drop the pressure by any amount in that particular system. This next graph and table shows us the UARL, the standard UARL, which is shown in grey. We've got UARL with SCF for FAVAD, which is the green curve, for FAVAD and Poisson, which is the purple curve, and FAVAD, Poisson and pressure bursts, which is the red curve. This graph shows the calculations for UARL in volumes, so in cubic meters per day. It also shows unavoidable background leakage. And in the original UARL equation, the unavoidable background leakage component was assumed to vary linearly with pressure. So on this graph, we do have a calculation for the unavoidable background leakage using an N1 of 1. But now we know that it actually behaves as variable area leakage. So we actually have in the light blue curve calculation specific for this particular system of unavoidable background leakage using an N1 of 1.5. Again, what you'll see is that as pressures as you go down to lower pressures, the lines and the curves get very, very bunched up together, very, very close. And so that's where the table is really good for interpreting the data. This graph and table are very insightful. You can get an awful lot of information from it. They allow you as well to approximately estimate the relationship between average pressure and UARL, and to derive that from the slope of the lines for any value of current average pressure. And an example of that is you would be able to calculate from this particular system that it's 8 cubic meters per day per meter of pressure for FAVAD, Poisson and pressure bursts at 35 meters pressure. Okay, so you can estimate the relationship between the average pressure and UARL with SCF from the slope of the line for any value of current average pressure. So our second example is, as I mentioned before, an exact fifth of the first example. So we're taking exactly the same average pressure, exactly the same percentage of rigid and flexible pipes, but we've only got 1,000 service connections and we've only got 25 kilometers of mains. So let's see how the calculation changes for this small system. So this slide takes the graph which plots system correction factor versus average pressure from example 1, 5,000 service connections on the left, and example 2, which is 1,000 service connections on the right, and compares them side by side. I've brought forward the actual values for the system correction factor with FAVAD, FAVAD Poisson, FAVAD Poisson pressure bursts for each of the calculations so that you can see them on screen. Okay. The first thing to note is that the two examples, the 5,000 service connections and the 1,000 service connections, both have a system correction factor when we just consider FAVAD of 0.90, and the lines are actually the same running through both. The shape and gradient of those lines are both the same, and they give the same value of system correction factor. What we're really interested here is the Poisson effect. And you can see here that the gap between the green and the purple lines, which shows the additional effects of the Poisson distribution, are very, very marked and definite when you look at example 2, which is the smaller system. So this is here to show how the Poisson effect has a bigger influence as system size decreases below 5,000 service connections. And the system correction factor, which only drops by 0.09 in our larger system, now drops by 23% in our smaller system. And if we look at the red curves as well, we can see on the left-hand side, if we look at pressures less than 50 meters, which this is an example of at 35 meters pressure, we go from 0.81 to 0.76 for FAVAD and pressure bursts at 35 meters, and on our smaller system, 0.67 to 0.64. But look what happens when you increase the pressure above 50 meters. So at 70 meters, we've actually got an SCF of 1.18 in our larger system. And in our smaller system at 70 meters pressure, we've got an SCF of about 0.99, just under 1. We can also compare the predicted breakdown of annual UARL bursts across both systems. The scale of these is obviously different between the larger and the smaller systems. And we did take a look at the burst frequencies for the first example a few slides back. But if we concentrate on example 2, our small system, this is a small system, so our UARL bursts will be relatively rare events, and that's reflected in the figures that you can see here. So the standard no adjustment for bursts, FAVAD only, 7.6 bursts approximately across mains and services, but this is a small system, so we see these numbers drop down when we consider the Poisson effect to the point that we've got 0.31 of a burst on our services to the property line to the meter. And then when we add in the pressure burst relationship as well, that reduces the overall bursts across mains and services to 3.3 bursts, UARL bursts per year. So In the last 9 months, we've completed calculations in a number of different countries that you can see here. And I just wanted to give you an idea of the diversity of those calculations. So they've covered DMAs as well as whole systems, anything from 120 to over 1 million services, with density of connections between 10 and 65 per kilometre. The service length from the property line to the metre of anything from 0 to 26 metres per connection, and the whole range of rigid and flexible pipes across mains and services, with average pressures in these calculations ranging from 25 to 100 metres. So, in summary, SCF allows the UARL to be applied to small systems, zones and DMAs. But the diagnostic approach and the information that you can gain from a calculation is useful for larger systems as well. It enhances but does not replace the standard UARL equation. You can find out more about Allan's research at the Leak Suite Library, and the links are on the screen there. The UARL software, although we've been demonstrating it in metric units, is also available online in US units. And as I mentioned before, unless your infrastructure changes significantly, then one calculation for a zone or a system or a DMA should be valid for several years. And you can find more information about the software, including a simulation you can have a go of at wlrna.com/software. So Allan and I are really grateful for your time and attention during our presentation this morning. I know that the IWA will post the video of this presentation on their YouTube channel. We'll also be putting copies of the presentation, the PowerPoint presentation, on the WLRNA website by the end of next week. So that's my section done, and now it's time to hand over to see if there are any questions that have come through in the chat window. Right, let's have a little look. The first question, Allan, is from Joe Parker. Just to clarify terminology, when Allan refers to bursts, does he mean all physical leaks or just eruptive failures?
I suppose, well, it depends what you mean by eruptive failures, but it's reported and unreported bursts, things you can actually detect, but not including background leakage. Some of them, as I say, will be unreported, some will be reported, some will surface, some will not.
Okay. Another question from Joe. Has Allan included any systems where the mains and services are all PE, which could theoretically achieve zero leakage, and where identifying leaks can be more problematical, leading to a different set of drivers for the number of leaks in the system? And will the pass-on effect be the same? Well,
certainly with the all plastic systems, the power law for those is 1.5. Now, you will also have background leakage. You have background leakage on any system. So I don't think I honestly don't think you can talk about zero leakage in systems. You can talk about a minimum level, how low you could go. And what it tries to simulate is that. And that's what we find with the all plastic systems. We looked at some in Austria, all plastic on mains and services, very small systems. And what you get there, you still have some leakage, but it tends to follow the 1.5 curve at different pressures.
Great, thank you. From Core, we've had a message: great work, research transferred into an applicable concept. Many thanks for sharing. From Ramesh Kumar, any study on systems having pressures between 10 to 20 meters?
No, nothing so far. And one's getting down there to, particularly with plastic systems, to ones where leakage detection can be very, very difficult indeed. We can extrapolate the curves down there. Actually, I think there was one that a colleague did in one of the islands in the Caribbean, and that was at a pressure of about 8 or 10. But that was we predicted that even though it was all flexible pipes, instead of being 1.5, when we apply the FAVAD, it would actually come down, that the N1 would come down to about 1, and that's what was found. So we could move cautiously in that direction, but I would stress move cautiously and check it out with some real data.
Okay, from Mohsen Jalili, what is the maximum value of N1? It seems that 2.5 is too high. Is there any evidence about this?
Yes, I think in tests which have been done, we very often get figures greater than 2. And I have a very strong suspicion now that it's because the tests, well, one way that can happen is that the tests are started too early while the consumption is still falling at night. And it's a common problem. And that's actually one of the next things that I'm working on at the moment, to come up with a similar software to this, to have a much more better quality controlled N1 test and calculation. So yes, I'm very suspicious of those high values now. I don't deny they can occur on occasions, but they are only occasionally. And I think it's a case of starting tests too early in many cases.
Okay, question from Paul Fanner. If you're using the system correction factor, why would you not include all 3 factors?
We just wanted to do all 3, but we worked on those in sequence, really. We first of all had the pressure correction factor for FAVAD, and then I decided to look at the effective Poisson. And then I thought, well, why not go the whole way and do the pressure bursts as well, which was missing from the first one. So we thought it good to be able to show people the 3 different figures and leave them to choose what they wanted to use. So in other words, if someone doesn't like the pressure burst relationship we've used, although we can change the coefficients, then they may only want to go as far as using FAVAD plus Poisson. And we do believe, I do believe in giving people choices for what they should use rather than simply offering them one solution.
Okay. Are there any more questions for Allan? Okay, this is an interesting one from Mohsen Jalili. Shall we think about a new performance indicator instead of ILI with less correction factors?
You could do that if you wanted to do to pull out about. You would probably need to have something like 18 to 20 different factors to put in to every calculation when you wanted to do a calculation, and you'd also have to use the full UARL component analysis concept, which would simply just put most people off from doing it. If you have to put in 18 to 20 parameters, then that's really a research rather than practical applications. I've always tried to bridge the gap between the theory and the practice so that people can use these things on the ground to get better answers if they want to. I also acknowledge that not everybody will want to use this URL with SCF, because if you're operating with an ILI of 4 or 6 or 10 or something like that, and you're trying to get down, then you don't need anything as sophisticated as this. But some people who have low ILIs and very small systems or very high pressures, they will probably find this useful. And that's why we say this is an optional customization of UARL. We don't want anyone to start thinking that everyone's got to do this. It's just those people who will find this useful to give them better targeting and better insights.
Thank you. Any more questions for Allan before I turn back over to Gary? No, I don't think there's any more questions, Gary, from the look of it, unless, hang on. Yes, from Satish Veggie. Hello, Allan and Kate. Are you thinking to consider soil movements or any such external factors on burst frequency?
Yes, in fact, that's another aspect of research I've been doing really for the last 20 years on pressure burst relationships and why we get them and how burst frequencies are changed when the the transients are reduced, but also when the static pressures are reduced. We'll be covering that to a small extent. I'm hoping sometime to do a webinar with Aravinda Stanley from Sydney Water on this particular topic. So I think it's probably best to leave that until there. But yes, there is work on that, which people may find of interest.
Great.
Okay. I think that's it. I think that's it, Kate. There's no more questions. So thank you very much, Alan. Thank you very much, Kate, for a great webinar. And just to let everybody know that we will be taking a break from the webinars leading up to Water Loss 2020 in November. But we're looking for people who wish to present any interesting topics we would consider. And we'll probably be back in December. Thank you very much.
Thank you.